Due to technical difficulties with this little box up here, we're only going to get one screen over on this side, so Murphy's Law, right? Okay, let's go ahead and get started. Today I'm here to talk to you a little bit about polymorphism and IDS and the response from intrusion detection systems to polymorphic attacks. Give a little bit about myself. I was in the Air Force for 4 years, had a great time, but they didn't pay me enough, so I got out. I was doing OSI investigations, information warfare, exploit intelligence. I moved to TriNet Data Systems, then moved on to L3, and then L3 was bought out by Symantec about 1.5 years ago. At Symantec, I do. Can you not hear me? Thank you. Can you hear me better now? Great. At Symantec, I am involved in signature development, IDS evasion, and engine development for our IDS product. So without further ado, let's go ahead and jump into polymorphism. We're going to take a look first at the evolution of malicious polymorphic code, starting with the virus back in the early 90s, and how the VA vendors were able to detect these. And then we're going to move into the paradigm shift, the shift that we see from actual polymorphic viruses to polymorphic attacks. We're going to be looking at some polymorphic coding, especially the ADM mutate tool by K2. I also want to mention that Drew last year talked about polymorphism at DEF CON, and a lot of this was based off of his work as well. We're going to look at some TCP dumps of polymorphic attacks, and I'll give you a demonstration of what the normal TCP dumps of an exploit is, and then a polymorphic TCP dump. And then we're going to be looking at IDS response. How can IDS respond to these types of attacks and the help that IDS is going to need in the future. So what is polymorphism? Polymorphism, basically, its Greek meaning is to have multiple forms. For most of you that actually develop an object-oriented program, polymorphism is basically the ability to process objects differently depending on their data type or their data structure. The polymorphism used here is a little bit different. It's not going against, it's not actually using the object-oriented programming values. Basically, it's continuous change. Polymorphism basically morphs regular expressions within the payload of an attack. And this has been able to exist on multiple platforms. Here we basically have the same output with different solutions. So basically I can say A plus B equals C and turn around and say A plus 3 minus 3 plus B equals C, and you get the same output. So with our understanding of polymorphism, let's jump into what happens in the virus world. The first of the viruses were considered simple viruses. Basically, it replicated itself, and these were very easy to detect. These viruses mainly were via floppies, program files, attachments within the emails. And right now, about 82% of all viruses out in the world are considered simple. These viruses can mutate with different viruses, and they both end up having characteristics of their parents. The virus here always makes an exact replica of itself, and the detection for the AV vendors were basically to scan for a sequence of bytes found in that virus. The next thing that came around in response to detection of simple viruses were the encrypted viruses. Basically uses a decryption routine to propagate the viruses across the network, and they hide the fixed bytes by encrypting this virus. Right here is an example of what an encrypted virus routine looks like. Here we have a virus decryption routine, and then we have the encrypted virus body. The encrypted viruses also consist of a decryption routine and an encryption body. It uses the decryption keys, but the decryption remains constant. So with that decryption, antivirus vendors were able to detect a sequence of bytes in the decryption routine and be able to alert on that particular virus. Basically, here's the flow of an encrypted virus. It executes its routine, then it gains control of the computer, and then decryption and gives control to the virus. Once the infection occurs, the virus then copies itself to files, programs, or whatever. And thank you. I need to turn mine off too. Then it copies itself, and then it re-encrypts itself and attaches it to a new program. The response to encrypted viruses were basically the polymorphic virus. And here, when a virus is executed, it will be decrypted to its original form so it can deliver its payload, but it contains a third iteration here that basically is a mutation engine, that generates randomized decryption routines with each individual use. The mutation engine and the virus body are both encrypted, so we had a hard time figuring out a fixed signature because each time that the virus was encrypted, the decryption routine was polymorphed, and that had a generated value each and every single time. So we had no way of really finding that virus by scanning it while it was polymorphed. This particular way it went about was it decrypted the virus, the mutation engine, then it transferred the control of the virus to the computer. It again copies itself, and now it copies the mutation engine and invokes the mutation engine, generates a decryption routine, and now the virus is now unique, and it attaches itself to a new program. So AV vendors were stumped at the very beginning trying to figure out how we can go about detecting these polymorphic viruses. And we're going to look here and try to figure out what we can learn from the AV vendors to help us in the IDS world. One of the first problems was, of course, Dark Avenger and his MTE engine with basically his polymorphic engine. This basically produced random programs, and it had billions of different variations. So AV decided to fight back by creating special detection routines to catch each polymorphic virus, and they were doing this by hand, and they were doing this by line. And this became very arduous. And when you're dealing with billions of variations, there's just no way that the AV vendors could keep up with this. They didn't have enough resource nor the time. So this was basically impractical, time-consuming, and very costly. So they had to move on. So the next thing that they tried to do was called generic decryption. And generic decryption relies on behaviors and techniques that trick the virus into decrypting itself and revealing itself within the program. What happened here was that these techniques, they decided to start using bits and pieces of the operating system and creating from memory a virtual machine, so that these polymorphic viruses would think that it was actually on the machine, and it would start decrypting itself in memory on the host, but not affect the host itself. It was separate allocated virtual machine. But the key problem here and generic description was speed. It was very slow, and having each program come in and try to run itself in its own virtual memory space became very unreliable and slow. Here, they moved on to heuristic-based generic description, which basically is a set of rules that differentiate non-virus from virus behavior and looks for that inconsistent behavior between those files. An example of a virus behavior is that a non-virus program will sometimes use results of math computations, while virus behavior files will do those same type of math computations but not use those results. So it was calculating all this stuff and not using it, trying to trick us into thinking that it was an actual good program. This also, the inconsistency increases the likelihood of infection here and prompts the scanner to extend time. When they see these types of computations, it tells the scanner to extend the time that the file needs to be in memory so that it can keep on executing that file in order to find triggers for that particular polymorphic virus. But also with this type of heuristic-based guessing, with the behavior techniques, AV vendors had to continual research and update. And the problem with this is that rules to detect 500 of these polymorphic viruses, when they went to update it, many times when they updated those rules, it altered the effects, and now we dropped 5 from the previous list. So when I'm updating with 10 or 15 new profiles to put into a virus detection routine with a heuristic-based detection, I might lose ground on previous viruses. This also relied on researchers to analyze millions of variations and extract a signature to modify the rules while guarding against changing previous rules. This also became the regression testing became very exhaustive, and soon this became obsolete and inaccurate. So the final solution that the AV vendors came up with, and what we can look at in the IDS world, and especially the network intrusion detection systems, is it relies on rules or profiles specific to each virus. The big ground here is that yes, it still loaded the file as we see here in a self-contained virtual memory or virtual machine, but it didn't rely on heuristic guesses. What it did is it rules out as many viruses as possible at first. So if this was a .exe, then we can rule out .coms, and we could rule out .sys, and we can rule out .bin, so we're only specific for the .exe files. And then it began to look for triggers. So basically what's happening here is the AV vendors began loading the file into a self-contained virtual machine, determining if this was a .com or .sys or .exe, and once they found that out, it was a .exe, then they knew that these specific virus, .exe virus, had these characteristics. And these characteristics could be A, B, C, D, or E. And the suspected file, when it observed A, then it knew that D, B, and E were out. So it just kicked it right out. And then it observed B, then the remaining of these 2 files are still in. So it still knows to keep on scanning for those triggers. And now it observed D, so we know that ABC is out and ABD is in. So that's just as simplistic as I can get it. for the way that they decided to do this. And the advantages of this became it was speed. It was a whole lot faster, and there was really no continual updating. It was just a plug into the profile. So now let's move on and look at the concepts used from polymorphic viruses to the concepts that are being used in polymorphic attacks going across the wire. Here we see that, of course, you have a mutation engine that basically starts morphing payload, shellcode, and things like that. We have a polymorphic algorithm, but here we're also morphing of the payload to include the shellcode, the no-ops within a payload. The encoder and decoder is also randomly generated, and we also have non-operational padding. The major intent of the polymorphic attacks is basically to evade signature analysis or pattern matching with an IDS system. Signature analysis basically looks at certain offsets or certain shellcode or no-ops or specific offsets within a payload. They can also look at the binary data. They can look at ASCII data, and they can look at headers, as for an example, for detecting exploits going across the wire. Signature analysis and passive protocol analysis together define event generations and analysis techniques that is used by the majority of the IDS vendors out on the market today. Passive protocol analysis or signature pattern-based analysis basically watches all traffic on the network and watches for patterns in that traffic for suspicious activity. So now that we have an understanding of what the polymorphism is trying to evade, it's the actual pattern matching of the shellcode, of the attack. Let's move into the encoding process that I've had time to research and see exactly what's being encoded here. The attack is morphed prior to launch, and with each subsequent morphing unique. So each time that you run an attack against a host such as DNS or SMTP, it's polymorphed all over again. Some methods used within the polymorphed is basically comes from assembly language, where you can have rotates, you can have moves, you can have left rotates, right rotates, which rotates binary data. The move basically makes a copy of the source and stores it into a different value. And also a big key here is with the XOR. And the XOR value here basically is a randomly generated value of XOR value. And what XOR does is basically takes the binary byte, and if the first or second operand, but not both, is 0, then the result is 1, otherwise the result is 0. The thing about this is that if we have a randomly generated XOR value of 23, and within the polymorphic attack, we have shellcode, and I'm using this from Snort, this particular shellcode that Snort's looking for on the TSIG vulnerability. Again, this is pattern matching here. We can take that shellcode that's highlighted there and bolded, and we can do an XOR value with an XOR value of 23. So what happens when you do that is now I have, instead of 3 F90s, I have 1C, B3, 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 and so forth. The major problem here is that when I have a value in my shellcode that can be any value from 00 to FF, and I XOR that with any value, my permutations are 255 factorial, which is a big number. And this causes great computational overhead for NIDS. Basically, the no operational assembly processor instructions here within the ADM mutate tool, he's basically substituting no known ops with other characters that don't affect the outcome of the code. We see no ops all the time in buffer overflows, like no op 90s going across the wire. Here are some platform-specific no ops that I have, and as we see, the intels are 90s, and usually there's only one or two registered or one or two published no ops for each platform, but here we have 3 for Spark. Some of substitutional no ops per K2, and also Drew helped him out on this as well, is here for Intel we have 49, 4B, 45, and we'll see those in the TCP dumps that I have. And there's some for Sparks. This can run on several different platforms. So we're not just Intel based here. My first thought when I saw this was, hey, let's take a look at the decoder encoder and we can detect it there. So I went and got I emailed K2 and said, hey, can you give me a copy of your ADM mutate? And he was courteous and nice and said, sure, here you go. So I started taking a look at it, and it turns out that right in his README file, I mean, he was already thinking about this. So unfortunately, that would be too easy for us to look for the encoder decoder. So the techniques used here are multiple code paths and randomly generated instructions to morph the encoding and decoding process of the shellcode. So here, let's get put this slide in so that we can understand we're no longer looking at the host here in polymorphism, we're looking going across the wire. So here we have an attacker, and then we have a network IDS in the middle sniffing packets, and then we have the victim themselves. So how can IDS vendors, network IDS vendors, go about detecting these polymorphic attacks? I'm sorry, let's look at TCPDumps first. Here, this is a TCPDump of an SMTP exploit. As we see here, we know it's IP, and we know it's 20 bytes long. I know it's TCP here, and I know it's headed for port 25. And I also know that here's our no ops. I did a lot of cuts here because there's a lot of no ops, and basically the shell code's in here that's doing the instructions. But here's what's interesting is, just so that you'll know, this is the bin shell going across port 25. So through pattern matching, this is really easily detected. It's not hard for IDS vendors to detect this. Here's a polymorphed one. It's the same attack, but it's been polymorphed. We still know it's IP. We still know that it's TCP. It's port 25, but here where all the 90s are is all the substitutional no ops. I cut it down again, and here's the shell code, and we don't see any similarities to the previous one at all. And it changes with each one. So as we see here, it's going to change again. So each time this goes across the wire, it's completely different. So that's how it evades pattern matching within IDS. One of the ways that we can detect this, and I want to harp on IDS vendors a little bit, is by using what we call protocol analysis. Protocol analysis basically looks at the application layer. What protocol analysis does is it breaks down the packets into manageable parts for its speed. If it's IP, then we look and see if it's TCP, UDP, and so forth. We find out that it's a TCP packet, And then we determine, where is it destined? Is it HTTP? Is it DNS? Is it FTP? What is it? Then we find out, okay, this is basically an HTTP packet, so then we apply our HTTP signatures to determine if the alert's needed. And that's protocol analysis in its simplest form, but the problem is that a lot of IDS vendors do this. But here we need to go further, because what's happening here is we're applying pattern matching signatures at the very end here. So when we go down and figure out by breaking down the packet into manageable parts that it's HTTP, we're just applying, is it CGI-BN-PHF or whatever. What I'm talking about is we're going to have to start looking at the RFCs. We're going to have to start determining exactly what the RFC says we can do and what we can't do. And by researching that, we'll be able to hopefully detect packets coming across the wire. But unfortunately, some of the major vendors specifically do not follow RFC guidelines. So we have to be more specific to the vendor with the way that they go about applying RFCs. By using this, we can, like I said, we can start looking for expected results. What we want to start doing here is we want to start looking for what the packet is like instead of what the packet is. And by doing this, protocol analysis can help us do that. Once we decide to look at these RFCs and once we decide to be able to create profiles for each particular protocol and be able to determine exactly what we should see and what we should not see, then we can start detecting these polymorphic attacks. Also, these will be proactive in a sense that once we figure out this stuff, we will be able to detect future attacks as well, not just polymorphic attacks, but future regular expression attacks. We get better performance out of this. It is harder to evade. But the problem also is what sometimes in the near future I see creating polymorphic code that actually looks like normal traffic. Here we go into pattern matching a little bit, and we can see exactly how polymorphism evades pattern matching. It searches for set patterns within the packet. I use snort here. We see here that the content of the TSIG LSD is actually a pattern matching contact looking for the shell code here within the named TSIG exploit. We also see the DDoS, the trouble flood network here by looking at the ICMP message. And of course we also see there's a pattern matching for looking at multiple no-ops going across the wire to any port. Here, binary signatures, we can start investigating binary signatures. It's more like a protocol analysis, but binary signatures, again, the good thing about the RFCs is that these RFCs are strictly defined, and attacks against text-only services could check for characters outside the standard text range, and we can pick up polymorphic attacks doing it that way. We also can look for packet size, POP3, RFC, things like that, can pick up these things by unusual large amounts of data streams. Here I thought of this one, connection time. We can look at abnormal connection time rates such as lengthy DNS collaboration, RPC, time-based. But this can be expensive because we're actually capturing the session. So that's another way that we can begin looking at detecting polymorphic attacks. Outcome detection, well, the problem with outcome detection is you've already know that you've already been attacked, and probably it's worked. But what we need to do is, intrusion detection system, especially the network, is just, it doesn't stop the attack, it just alerts you on the attack. Here we're able to see the response of attacks. Some way we can detect, we see a bin shell or detect collaboration coming across from port 53 from your DNS server. Another evasion technique here is the response from the victim being hashed, being encrypted, and being scrambled. So that could be another evasion technique for outcome detection. Here I took the last stage of delirium to show you a little bit of outcome detection in its simplest form. Here we see no ops going to the server, and we see bin case shell going to the server, and we see uname -a going to the server. Okay, so that's all headed toward the server to do a buffer overflow, basically. The response that we get back from those is the response to the uname -a, and also the response to such things as cat etc password. So if you see cat etc password or anything that's abnormal out of the range coming from your DNS port, you know you have a problem. Now we're going to get into some help. I believe that IDS is going to need help, and a lot of security experts have hounded on this for a long time, is that you need a suite of tools. You need a suite of tools to be able to help you try to make your networks inviolable. So here with log analysis, we were able to, such as var ADM messages and varlog syslog, we were able to detect possible polymorphic attacks by messages going into the logs, even though we didn't see it come across the wire through our IDS. Here we see a child process daemon being spawned from desktop management interface. And this was the desktop management interface buffer overflow that was recently released. Again, this deals with host-based intrusion detection systems that help us detect these types of things. Changes to any audited file, spawning of child processes, removal of these files. Even though we don't see it or we don't have it through the IDS side, we are still able to detect it possibly through the host-based side. We can look at unusual port activity as well. RPC, such as TDDB, active sessions to outside hosts. You can create profiles saying I should not see any port maps, or I should not see any port maps to port mapper at all from any host other than my network. So basically what we have here is a feature of tools that we can use to detect polymorphic attacks. And we have protocol analysis that needs to be improved by IDS vendors. We have outcome detection. We also have host-based IDS that can help us. The reason I put firewalls up here is I was able to create, using the ADM mutate tool, I was able to use its API and put it into the TSIG vulnerability. I tested this polymorphic exploit against some major IDS players, such as ourselves, NetProwler. I tested it against Dragon. I tested it against ISS, and I tested it against Snort. And to no avail, none of us detected it. We didn't even see it, although they did detect the TSIG exploit. So none of the vendors detected this whatsoever. But what was funny is I decided to put a proxy-based firewall in between that and the host. And through my investigation, the proxy-based firewall was dropping this packet. So it wasn't able to get through, it wasn't able to get through the firewall. And those are on proxy-based. And what the proxy-based firewalls are doing are just basically taking RFC standards and it's doing, I'll answer your question in just a minute. It's using the proxies to determine if this packet is a good packet or a bad packet. Also, security experts talk about this as well, is vulnerability assessment. I mean, if we're patched, your likelihood of getting attacked is you still might get attacked, but it's less than the likelihood of you being attacked without any patches on your system. Assessment and intrusion detection on the host-based and the network-based is what's going to help us here. And with firewalls, a host security solution. We can be proactive, and also we can be reactive at the same time. I got in a conversation with Elliot Turner last night about and he's from intrusion.com, about the state of network IDS detection is where antivirus was 5 years ago. And we got into a conversation about this, and it basically turned out that there are some vendors out there that are actually trying to improve protocol analysis. And what I'm trying to do here is get the other vendors to take notice and start improving their protocol analysis as well. I believe IDS evasion is just now getting started. We're going to see more of this in the future, especially now that K2 has incorporated a morphing engine into an API that you can plug in. I see a lot of these polymorphic attacks hitting the wire in the next 6 months. If you want a good briefing, a technical briefing over the ADM mutate tool, K2 will be speaking at DEF CON at 6 o'clock on Saturday. So he will give you a more detailed explanation exactly of what his tool is doing. Also, I believe that within the next 6 months to a year, we're going to start seeing polymorphic worms. So, that's basically the end of my presentation. I do have one thing here is a shameless promotion thing. A friend of mine named Kevin Mandia from Foundstone used to be in the Air Force, and he just released a book. It's a good book. Incident Response, Investigative Computer Crime, and this basically is basically what he did in the Air Force. My credits, I'd like to thank K2, I'd like to thank Jeru for his input, I'd like to thank Elliot Turner for his input as well, Snort. I'd also like to thank SARC, and also like to thank Symantec as well. So with that, I am open to questions. Yes, sir.
Just a comment on the RFC statement that you made. As an implementer of RFC protocols, a lot of times the RFCs are not very specific. And if you attended the session in the last hour about ICP, fingerprint, hosts, and there's lots of stuff where the RFCs are not specific about how to handle faulty input and how to handle certain cases.
Agreed. But this is a...
All I'm saying is that adhering to RFCs is not going to do much. You're going to end up having more specific.
Agreed. And RFC is a good starting point for us. So, and that's why I mentioned it. It's a good starting point for each individual protocol.
I'll mention one other thing, and that is most vendors will extend a protocol in some way, and they'll either publish that or they won't publish it. So,
sort of like, yeah.
You're talking about application layer protocols, so then you actually have application versions that you'll end up having to detect.
Right. Yes, sir.
Question for you, actually, on this one, and it's part of my policy also. Instead of always doing the exclusion things, looking for the unusual, or excuse me, looking for specific patterns and attacks and so forth and so on, could you not reverse it and look for normal patterns of usage and then look for anything that is out of the ordinary?
Yes.
What my DNS server suddenly starts sending out 8K packets, or suddenly starts trying to do other oddball things aside from here I'm going to tell Tom, I'm this, I'm this, I'm this, and then see password about it.
Right. Yeah. Right, and we can do that. It just depends on, it really depends on the protocol that we're dealing with. There are some instances that we have done that before. We're looking for the good things instead of the bad things, because there's so many bad things, it's better for us to look for the good things. So that has been done before, yes. Yes, sir. The result of my research is not published yet. I plan on updating this presentation to include actual attacks going against the major IDS vendors and actual attacks hitting firewalls. So my results are not out there yet, but they will be. My email address is at the very beginning. Oh, by the way, this is an updated presentation. I'll be emailing it to Black Hat. My email address is at the beginning of the presentation. It's cskipper@symantec.com, but it will be my results probably will be posted at Symantec somewhere in the near future. Yes, sir.
So what are the performance issues with decoding on the application layer? Seems like Snort, Martin Morrison is talking about, just the significant performance impacts that you start seeing when you start doing the higher levels of checks. Application gateways, obviously, a big difference in performance between them and the stateful packet filters. How is these IDS that you're talking about to be able to do that in a higher bandwidth network the same day?
Well, the performance issues I was talking about was basically breaking down the packet into manageable parts. And you're only applying those particular, once I break it down into, go all the way down to an HTTP stream, then I'm only applying my particular signatures against that particular attack coming across the wire. So therefore, I'm not applying my 1,600 signatures against it. I'm applying only about 50 or so against it. So the computational overhead is less, and my ability to keep packets coming in is greater.
That's the optimization, though, a proxy does. An HTTP proxy can do FTP checks.
Right.
So, they're still having the same performance problem.
Yeah, we're still having the same kind of problems. Anything else? Yes, sir.
How many attacks have you seen through an SSL, inside an SSL channel?
I haven't seen very many, no. In fact, I haven't seen any. And that's the thing about IDS. With encryption and SSL, you're not going to be able to see any of that.
I don't mean an IDS, I mean how many attacks do you know about just in general that happen through an SSL session?
I don't know of any.
Seems like any HTTP buffer
tunnel on your local box, and then when a whisker through your local connection, it'll go off SSL.
Right. So I mean any web attack that happens with SSL.
Okay. All right, thanks for coming.